This is Calculus 2 video lecture number 3 on trigonometric substitution. Now, trigonometric substitutions are going to be used on integrals whose integrand involves a radical function whose radical is the difference or sum of squares. Okay, and there's a few cases, 3 in particular, that you need to be able to identify and then know what the appropriate trigonometric substitution is. There are a few cases where you can apply it for integrals that don't involve radicals, and we can look at those later, but this is, for the most part, the primary function of them. So case 1, if your integrand has the form rad a squared minus x squared, where a is a constant, then what you're going to do is use the substitution, letting x equal a sine theta. And you need to restrict the domain to negative pi halves, including that, and pi halves. That way you're in quadrants 1 and 4, restricting the domain on theta. And then you're going to use the identity 1 minus sine squared theta equals cosine squared theta to simplify the integrand. Okay, this will make a lot more sense once you see an example, so let's just dive right in. So we're going to evaluate the following integral. We've got integral of x cubed times radical 9 minus x squared. Now, you don't want to jump to trig substitution as your first method of integration, right? When you first look at this thing, you go, oh, could I use sub? It's not looking like it because I've got an x cubed out here, not just an x. Maybe I could break it up, but that's looking a little messy. But notice here, this is a nice expression that we could use for a trig sub. So in this case, a is equal to 3, right? Since we have a squared minus x squared. So what I'm going to do is let x equal 3 sine theta, all right? And now I have to change my whole integral so that it's in terms of theta. It's not like a u substitution, it's different. Then I'm going to find dx, so dx is going to equal 3 cosine theta d theta. All right. So now I know what I'm going to replace dx with. Now let's figure out how the quantity underneath the radical is going to simplify. I have rad 9 minus x squared. And since I'm letting x equal 3 sine theta, that's going to be rad 9 minus 9 sine squared theta. All right, well, I can factor the 9 out from both of those quantities. So I'm going to have radical 9 times 1 minus sine squared theta. And this is going to give me 3 rad cosine squared theta. And please be so careful when you have the square root of cosine squared theta. That's the absolute value of cosine theta. Do not forget those absolute value bars. Well, how do I know whether or not to use positive or negative cosine theta? Do I have to split this into 2 integrals? No. Remember, in this case, at the very beginning, we restricted theta between pi halves and negative pi halves, quadrants 1 and 4. So in those quadrants, cosine of theta is greater than or equal to 0, which means I know I'm just going to use positive 3 cosine theta. So that takes care of the quantity underneath the radical and the radical as well, right? We took the square root. So that's all taken care of there. dx I have, that's right here. That's 3 cosine theta d theta. Who's left? Yes, poor little x cubed. Okay, so x cubed is going to be 3 sine theta cubed. So that's going to be 27 sine cubed theta. So now it looks like everyone's accounted for, right? X cubed is going to get replaced with 27 sine cubed theta. Okay, so here we go. Let's put it all together. I'm going to have integral 27 sine cubed theta times, and then next piece is the rad 9 minus x squared. Well, that's replaced with 3 cosine theta, and then dx gets replaced with 3 cosine theta d theta. Fabulous. All right, as soon as I see an integral like this, I go, ooh, we're taking all these constants outside. We don't need them harassing us, making a big mess. So 27 times 3 times 3, that's 27 times 9. So we've got a 243 sitting out here. And then I have a sine cubed theta, cosine squared theta, d theta. All right, now let's think back. Do we know how to integrate this expression? Why, yes, we do. We just did a whole lesson on trig integrals. Remember, when you have a product of powers of sines and cosines, you factor out one of the factors on whichever trig function is raised to an odd power, right? You take the odd man out. In this case, since sine is raised to the third power, I'm going to rewrite this as 243 integral sine squared theta cosine squared theta times a sine theta d theta, like that. All right. If you didn't watch that video yet, I'll link it up here. It's one of the very first cases we consider. Okay, why do we pluck off one of the factors of sine? Because remember, we want this sine theta d theta to get absorbed as du. So that means we would need to let u equal cosine theta, and then du would end up being negative sine theta d theta. Okay, no problem. So we've got an extra negative in there. Also, if u is cosine theta, then I want to replace this sine squared theta with 1 minus cosine squared theta. Okay, so before we make this substitution, let's get everything set up. So we have 243 integral. Sine squared theta is getting replaced with 1 minus cosine squared theta. Then I still have that cosine squared theta sitting there and sine theta d theta. Beautiful. All right, so here we go. Now, du is negative sine theta d theta. So I'm going to replace this, but I'm going to add a negative in my integral. So I'm going to have negative 243 du. All right. And then 1 minus cosine squared theta, this is going to get replaced with 1 minus u squared. And then cosine squared theta is just going to get replaced with u squared. Okay, there's that. There's that. Color coding it all so you can see where everybody went. Okay, good. Now let's see, how would we deal with this integral? So I have negative 243 times, distribute that u squared. So this is going to be u squared minus u to the fourth du. If you want to get rid of that negative, you can reverse the order of subtraction, right? So this is positive 243 integral u to the fourth minus u squared du. Oh, that looks so much better. Plus it's in descending order now, right? Great. And then this is going to be 243 times u to the fifth over 5 minus u cubed over 3 plus c. All right, very good. Now we're going to go back and replace u with cosine theta. So now I have 243. This is going to be cosine to the fifth of theta over 5 minus cosine cubed theta over 3 plus c. Are we done? Should we box it up and call it a day? Remember, the original integral was in terms of x. So how do we get back to x land? We'll go back to where you started with. We started with letting x equal 3 sine theta. So I want to replace all of the thetas now so that everything's in terms of x. You have to draw a triangle. Pretend you're in a trigonometry class. So that means x over 3 is equal to sine theta. Let's draw a triangle. Here we go. There, much better. Here's our right triangle. Here's theta. So sine is the ratio of the opposite over hypotenuse. And that means the remaining leg is going to be rad 9 minus x squared. Here's a cool tip. The side that you solve for should be the expression that was in your original integral. If not, go back and check something. Okay, well, how am I going to use this triangle? Well, can I figure out what cosine of theta is now using this triangle here? I sure can. So cosine of theta is adjacent over hypotenuse. So cosine of theta is going to be rad 9 minus x squared over 3. Whew, okay, so here we go. Let's sub it all in. So we've got 243. Let's distribute it like this so we don't have to deal. So 243 over 5, and then cosine of theta, which is rad 9 minus x squared over 3. This is all raised to the 5th, minus 243 over 3. And then here I have cosine of theta cubed. Okay, so cosine of theta was rad 9 minus x squared over 3, and now we're cubing this guy, plus c. All right, can we clean it up a wee bit? I certainly hope so. 3 to the 5th is 243. Did you know that? I hope so. If not, you got a calculator, so you're okay. So 3 to the 5th and 243 are going to cancel out. That's gone. And then you have 9 minus x squared, square root of that raised to the 5th. So if you raised it to the 4th power, that would just be 9 minus x squared squared, and then you've got one more radical left over. So this is going to be 1/5 9 minus x squared squared times rad 9 minus x squared. All right. And then let's see what cancels out over here. So 3 cubed, that's 27. And then I've got another 3, that's 81. So 243 divided by 81, excuse me, is 3. So I have minus 3. And then let's think here. If I have rad 9 minus x squared cubed, then I'm going to get 9 minus x squared to the 1st power, and then another rad 9 minus x squared plus c. And that's your final answer. Okay, let's box it with pride. I mean, that was a labor of love right there. Good. So just be super careful after you use a trig sub. If it's an indefinite integral, you have to go back, draw that triangle, and rewrite everything in terms of the original variable. All right? Good. So that's the first case. Do you remember what it was? A squared minus x squared underneath the radical. Okay, case 2. The integrand has the form radical a squared plus x squared. Instead of subtraction, it's addition. So you're going to use the substitution x equals a tangent theta, and then restrict the domain on theta to negative pi halves and pi halves, not including pi halves or negative pi halves because tangent's undefined there. And then you're going to use the identity 1 plus tangent squared theta equals secant squared theta to simplify the integrand. All right, so here we go. We have integral from 0 to 1 of x times radical x squared plus 4 dx. Okay. Now, I'm going to demonstrate the method of trig sub here, but think about there might be another way to do this integral. So starting off, I'm going to let x equal 2 tangent theta, right? That's a squared right here. This 4 is a squared. All right, so find dx first. So dx is going to be 2 secant squared theta d theta. So this is taken care of. I'm going to replace it with 2 secant squared theta d theta. Now let's see what's underneath the radical. So we have radical x squared, so that's going to be 4 tangent squared theta plus 4. And then I can factor out the 4. So I have radical 4 times tangent squared theta plus 1, which is going to be radical 4 secant squared theta, which is, be careful, do you remember, 2 absolute value of secant theta. And then remember, we restricted our angle between negative pi halves and pi halves. So again, we're in quadrants 1 and 4. Cosine's positive there, so secant's going to be positive there as well. So we have 2 secant theta since we know theta is between negative pi halves and pi halves. All right, so now I know I'm going to replace this entire expression here with 2 secant theta. In this case, I have limits of integration, so I need to figure out what those new limits are going to be in terms of theta. So let's go ahead. Be careful, you're not plugging in, you're setting it equal to the value. What do I mean by that? Well, these limits are in terms of x, right? So when x equals 0, remember x is 2 tangent theta. So that means tangent theta is 0. So what would theta have to be? You're not plugging in 0 for theta. No, no, no. You just think of your unit circle. Theta would be 0. Okay, that one wasn't bad. Now the other limit of 1, when x is 1, that means 2 tangent theta is equal to 1, which means tangent theta is a half. That's not any nice angle on the unit circle. So you're just going to say, all right, theta is tan inverse of a half. That's our new upper limit. So here we go. Let's switch everything so that it's in terms of theta. So we've got integral. I'll rewrite the original. 0 to 1, it was x times radical x squared plus 4 dx. Okay, so new limits. New lower limit, 0. New upper limit is tan inverse of a half. X gets replaced with 2 tangent theta. Rad x squared plus 4 gets replaced with 2 secant theta. And then do you remember what dx gets replaced with? We did it first. 2 secant squared theta d theta. Okay, here we go. Let's see, take those constants outside, right? We don't want them bothering us. So I'm going to have 8 integral from 0 to tan inverse of a half. And then this is going to be tangent theta times secant cubed theta d theta. Do you remember this case, what you're supposed to do? You're going to pluck off one factor of tangent, one factor of secant, so you can make a u substitution. Woo! So this is going to be 8 times the integral 0 to tan inverse of a half. And then I'm going to take off one factor of tangent and one factor of secant. So I'm going to be left with secant squared theta times tangent theta, secant theta, d theta. Why do I do that? Because I want this to be absorbed in my du, which means I would need to let u equal secant theta. And then du would be secant theta, tangent theta, d theta. All right? Very good. Okay, from here, let's figure out what our new limits of integration are going to be if I change this whole integral to be in terms of u. Okay, so the limits u of, now I plug it in, right? This is a different substitution. So u of 0 is equal to secant of 0, which is 1. And then u of tan inverse of a half. My goodness, how do you do that? So that's going to be secant of tan inverse of a half. And then you think back to trig days, pre-calc days. Yes, it's triangle time again. Woohoo! So here we go. This represents some angle, right? This is my theta. So tangent of theta is a half, which means ratio of opposite over adjacent is a half. Hypotenuse is going to be rad 5. Now, can you figure out what secant of that angle is? Secant's going to be hypotenuse over adjacent. So that's going to be rad 5 over 2. And there you go. There's your new upper limit. New upper limit, new lower limit. See how important trig is? Okay. So let's rewrite our integral now, all in terms of u's. The 8 just comes along for the ride. Sit tight, 8. Here we go. So we've got 8 integral 1 to rad 5 over 2. Secant squared theta. That's just going to be u squared. And then tangent theta, secant theta, d theta is du. Whew, the worst is over. Look at this cute little integral. We got this, no problem. Add 1 to the exponent, divide by the new exponent. This is 8/3 u cubed, evaluated from 1 to rad 5 over 2. Okay. So we've got 8/3 times rad 5 over 2 cubed minus 1 cubed. So this is 8/3 times rad 5 cubed. That's going to be 5 rad 5. 2 cubed is 8 minus 1. And then let's distribute the 8/3 because it's going to cancel so beautifully, right? So we'll have for our final answer 5 rad 5 over 3 minus 8/3. So 5 rad 5 minus 8 over 3. And we are done. Fabulous. Did you ever anticipate trigonometry to come back with such a vengeance in calculus? All right, let's look at another example with this same case that's a little more fancy. Okay, it's time to kick it up a notch. So we're going to evaluate the integral, and I've put in a nice little hint for you. You need to complete the square. The square underneath the radical, that way it could have the form x squared plus a squared, right? So do you remember how to complete the square? If you have x squared minus 6x, what constant would I need to have a perfect square trinomial? You take the coefficient of the linear term, divide it by 2, and then square it. So I would need to have a 9 in order to be able to factor this into x minus 3 squared. Okay? Well, notice here this is 13. So I'm just going to steal 9 away, and then I have plus 4 left over. Oh my, that's convenient, right? So I can let x minus 3, just treat that as one whole quantity, right? Instead of x, now we have x minus 3 equal to tangent theta. So a is going to be 2. You see that? It's a little different than before, but the rest of it just falls into place the same way. So you're going to find dx, derivative of that negative 3 is 0, so you're just going to get dx equals 2 secant squared theta d theta. See? No big deal. Okay, so now let's go ahead, see what's going to happen in our integral. So we have integral of dx. I'm first going to rewrite the denominator as radical x minus 3 squared plus 4. Okay, so dx in the numerator is going to get replaced with 2 secant squared theta d theta. And then in the denominator, we have that rad x minus 3 squared. So if I square x minus 3, I'm going to square 2 tan theta. So that's going to be 4 tan squared theta plus 4. All right. And then remember, I can factor that 4 out, and then I have tangent squared theta plus 1. Good. So next step, let's clean up a little more. We've got integral 2 secant squared theta d theta over radical 4, and then now I can replace tan squared theta plus 1 with secant squared theta. Okay, and then remember, this is going to simplify for us. I've got 2 secant squared theta d theta over, it's 2 absolute value secant theta, but we know we're going to choose the positive because we restricted theta. So I just have secant theta and a 2 in the denominator. One of them's going to cancel out. And then you just have the integral of secant theta d theta, right? And the 2 cancels as well. Woo! Do you remember what this is? I told you to memorize it just because it's going to come up so often and you don't want to have to do that funky little u substitution every time to remind yourself. You probably won't remember how to do it if you don't even remember what the integral is. So it's natural log, absolute value, secant theta plus tan theta plus c. Are we done? Surely I feel like this problem has gone on long enough. No, no, no. The original integral was in terms of x, so I have to rewrite everything with respect to x in terms of x. So here we go. Go back to the original substitution. Remember, we let x minus 3 equal 2 tan theta, which means that tangent of theta equals x minus 3 over 2. So it's triangle time. Here's theta. Tangent's going to be ratio of opposite over adjacent. And that means the hypotenuse is going to be rad x minus 3 squared plus 4, which we know before we completed the square, it was x squared minus 6x plus 13. Okay? So now I'm going to come back to the integral, replace everything so it's in terms of x. So secant of theta, that's going to be the ratio of the hypotenuse over the adjacent side. So that's going to be radical x squared minus 6x plus 13 over 2. Plus, and then tangent theta, I already have that. That's x minus 3 over 2 plus c. Okay, you're not done. You can clean this thing up, and it's important that you do so. So notice, I can write these with a common denominator. So I have ln, absolute value, radical, x squared minus 6x plus 13 plus x minus 3 all over 2 plus c. And then you can use your properties of logarithms and rewrite this as natural log, absolute value, radical, x squared minus 6x plus 13 plus x minus 3, and then I'm going to subtract the natural log of 2 plus c. And really, natural log of 2 is just a constant. So I can absorb it with the plus c and have a much cleaner expression. So make sure you do this. And this is just going to end up being natural log, absolute value, radical x squared minus 6x plus 13 plus x minus 3 plus d, where d is equal to c minus natural log of 2. So when you check your answers, typically it'll just have this cleaned up version, but they'll probably swap out d with c. So if you want to do it so that yours also has a c at the final step, all you would have to do is change it earlier. So you could say, call that instead d, 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 or whatever you want. And then this you could make a c, if it bothers you that it's not c at the end. It doesn't matter. It's just plus a constant. You just got to remember to do that. Okay, I'm leaving it alone. It's good. All right. Let's look at another one where we need to complete the square before we move on to the third and final case. And I want to demonstrate this one because I did mention at the very beginning that sometimes you'll use these trig subs even if there isn't a radical, right? So even if there isn't a radical, I'm looking at this and I've got this quadratic expression in the denominator and it's not looking like a u sub's going to help. You always want to see if I can do a u sub first because that's the easiest, most straightforward way to anti-differentiate. But if it doesn't, then you have to get out your more fancy tools. Okay. Can we complete the square for 3 minus 2x minus x squared? It's a little tricky. You got to factor that negative out of the x's. So when you have 3 minus 2x minus x squared, you're going to rewrite that as 3 minus, I'm going to have x squared plus 2x. And then remember, divide the linear term's coefficient by 2 and then square it, so I'm going to add 1. But really, that's a negative 1, isn't it? Because of this minus sign sitting out here. So now I have to add positive 1 to compensate. So combining my constants together, now I have 4 minus x plus 1 squared. Beautiful. Okay, this is the first case that we looked at, right? Using sign, when you have a squared minus a variable squared. So I'm going to let x plus 1 equal 2 sine theta, and then dx is going to be 2 cosine theta d theta. Okay, so let's go back to our integral. Now we have integral of x over, I'll replace the denominator now with 4 minus x plus 1 squared dx. Okay, so in the numerator I have just a plain old x. So that's going to get replaced with 2 sine theta minus 1. Do you see that? Be careful. And then in the denominator, 4 minus x plus 1 squared, that's going to be 4 minus x plus 1 was 2 sine theta, so this is 4 sine squared theta. And then dx over here, dx is going to get replaced with 2 cosine theta d theta. 2 cosine theta d theta. Good? All right, let's see. What cleaning up can we do? So we have integral 2 sine theta minus 1 over 4 minus 4 sine squared theta. That's 4 cosine squared theta. And then here's 2 cosine theta d theta. So I can cancel out a cosine. That's good. I can also cancel out this 2. And now the 4 in the denominator becomes a 2. Okay, so let's split this up. Notice we've got 2 sine theta minus 1 in the numerator, and then I have 2 cosine theta in the denominator, d theta. And a u sub won't work. Like if I were to let u equal cosine theta, du would be negative sine theta, but what would I do with that minus 1? I'm stuck. So I'm going to split this integral, split the numerator like this. I'll have 2 sine theta over 2 cosine theta minus 1 over 2 cosine theta. And then you have just d theta hanging out there still. Don't ever forget it. Especially because now we're so fancy, right? We go dx to d theta to du all in one problem sometimes. Okay, this is looking good because now I have integral. These 2's are going to cancel. So I just have tangent theta minus 1/2 secant theta d theta. Do we know these antiderivatives? I hope so. So antiderivative of tangent theta, natural log, absolute value, secant theta, minus 1/2, we just did secant theta, natural log, absolute value, secant theta, plus tangent theta, close it up, plus c. Beautiful. Now remember, our original integral was all in terms of x. So we have to draw a triangle so we can switch back to x land. So here we go. We remember, x plus 1 equal 2 sine theta, which means that sine theta is equal to x plus 1 over 2. So it is triangle time. Triangle time, so fun. And here's theta. I'm going to have opposite, which is x plus 1 over hypotenuse. That means the other leg is going to be 4 minus x plus 1 squared, which is rad 3 minus x squared minus 2x. And remember, that leg, that remaining side, should always match up with an expression that was in your original integral. Okay, so here we go. Now let's switch everything. So I have natural log, absolute value. Now secant theta is going to be the ratio of the hypotenuse to over the adjacent side. So that's going to be 2 over radical 3 minus x squared minus 2x. Okay, minus 1/2 natural log. I have secant theta again, so I just found it. So 2 over radical 3 minus x squared minus 2x plus, and then tangent theta. So tangent theta is going to be opposite over adjacent. So that's going to be x plus 1 over radical 3 minus x squared minus 2x, and then plus c. Okay, so now we have to clean up. First thing you want to do, we know using our properties of logarithms, I could move that 1/2 coefficient as the exponent here, which means I'm going to take the square root of it all. Okay. Also, I can combine these in the numerator because they have a common denominator into x plus 3. So we have natural log absolute value 2 over radical 3 minus x squared minus 2x minus natural log. Now in the numerator, I'm going to have x plus 3 when I combine like terms, and then since I'm moving that 1/2 coefficient to the exponent, now I have the square root of that, over common denominator already has a square root, so if I take the square root of a square root, now it's the 4th root of 3 minus x squared minus 2x plus c. Okay, notice we have subtraction with two logarithms, so I can combine them if I divide the arguments, which means I'm basically just going to multiply by the reciprocal of this argument. So what's happening here? So we've got natural log. I'm going to have 2, then the 4th root of 3 minus x squared minus 2x is going to come up to the numerator. And then in the denominator, we're going to have radical 3 minus x squared minus 2x. And then rad x plus 3 is going to come join it there. That's a 3. Please stay a 3. Plus c. Don't forget the plus c. Okay, we can still clean up because remember, when you have the square root, this is 3 minus x squared minus 2x to the 1/2. And this is that same expression raised to the 1/4 power. So I can cancel, right, or subtract the exponents, and I'm just going to have the 4th root left over in the denominator of 3 minus x squared minus 2x. So in the next step, I'm going to write natural log absolute value of 2 over, here, I'll switch colors so you see what's changing here, 4th root of 3 minus x squared minus 2x, and then leave the radical x plus 3. Okay, so basically you canceled out 1/4. There were more in the denominator, so that's what's left over, plus c. Anything else you notice you can do? Well, let's split it into subtraction because this is just a constant. Do you remember doing this a little bit? So we're going to have natural log of 2. I don't need absolute values because I already know there's no variables in there anymore. That's positive. Minus natural log. Do I need absolute value if I'm taking even roots, 4th root and square root? No, those are always going to be non-negative. So we've got, in fact, they're not even going to be 0, right? Because we've got a constant under each of them. Perfect. 4th root of 3 minus x squared minus 2x and square root of x plus 3 plus c. And then look, look, look. This is a constant. Let's absorb it with the c. So now I have negative natural log 4th root of 3 minus x squared minus 2x radical x plus 3 plus d, where, if anyone cares to know, d is c plus natural log of 2. That's just being a little extra, but we love it. Okay, good. There's a lot of nuanced little computations going on. Don't let yourself get overwhelmed. Just say, I am an advanced calculus student. I can handle this. All right, are we ready for the third case? Good, here we go. Now we are on our third and final case for trigonometric substitution, and that is when the integrand has the form radical x squared minus a squared. So you're going to use the substitution x equals a secant theta, and we restrict the domain of theta to 0 to pi halves union pi to 3 pi over 2. So this is in quadrants 1 and quadrant 3. All right. And you use the identity secant squared theta minus 1 equals tangent squared theta to simplify the integrand. And notice in both quadrants 1 and 3, tangent of theta is positive. So just be careful. You use this substitution when you have the variable squared minus the constant squared. If it's the other way around, that's when you use a sine theta, if it's the constant squared minus the variable squared. All right, here we go. Example 5, evaluate the integral from 1 to 2 of radical x squared minus 1 over x dx. So we're going to go ahead and let x equal 1 secant theta, and so dx would be secant theta tangent theta d theta. Let's see what our radical expression would simplify to. So we've got rad x squared minus 1, that would be secant squared theta minus 1, which is square root of tangent squared theta, which is absolute value of tangent theta. But remember, we restricted theta to quadrants 1 and 3, where tangent is positive, so this is just tangent theta. Okay, good. Now let's take care of our limits of integration. So when x is equal to 1, that means secant of theta is equal to 1, which means cosine of theta is 1, if that's easier for you to think of. So that happens when theta is 0. And then when x is equal to 2, that means secant of theta is 2. Again, if it's easier, you could think of this as the same as when cosine theta is a half. And that happens when theta is pi thirds. So that's my new upper limit. All right. Let's rewrite everything in terms of theta now. So we've got new lower limit of 0, upper limit is pi over 3. Radical x squared minus 1 gets replaced with tangent theta. Boom. Over just plain old x hanging out down there. Hi x, what are we going to replace you with? Secant theta. All right. And then I still have that dx. And dx is secant theta, tangent theta, d theta. Secant theta, tangent theta, d theta. There we go. Everybody's accounted for. All right, now we can have fun and integrate. So secant theta cancels out. It's very satisfying. And then now we are left with integral from 0 to pi thirds. I have tangent squared theta, d theta. What to do? Just use a trig identity. Don't overcomplicate this one. We've got 0 to pi thirds. I can replace tangent squared theta with secant squared theta minus 1 d theta. Can we anti-differentiate? We sure can. Antiderivative of secant theta, that's just tangent theta, minus antiderivative of 1 is going to be theta. Evaluate this from 0 to pi thirds. And so we're going to have tangent of pi thirds minus pi thirds minus lower limit tangent of 0 minus 0. Don't be lazy and just assume the result of plugging in the lower limit's always going to be 0, especially with these trig integrals, right? If you got a cosine in there, be careful. Anyways, not the case here. This is all 0, but be alert. And then tangent of pi thirds, that's going to be rad 3 minus pi thirds. We'll just leave it like that. Beautiful. Okay, so you have all three cases now. We're going to look at just one more example, a little bit of combo of integrating techniques. You have to bring your A game. So evaluate the following integral from 0 to pi halves of cosine of t over radical 1 plus sine squared t dt. What in the world? Okay, now notice in the denominator you've got this radical expression, so you're feeling like you need to do a trig sub, but you're not quite at that point yet, because instead of having x squared, we have this sine squared t. So maybe let's do a u sub first so that it looks more familiar, and then we'll go ahead and see if trig sub is going to help us take it home. So I'm going to start off and just say, all right, let's let u equal sine t, and I feel like that's a good choice because I noticed that little cosine t sitting up there in the numerator. So du is going to be cosine t dt right here, and then let's figure out what our new limits of integration are going to be. So u of 0, the lower limit, is sine of 0, which is just 0. And then u of pi halves, the upper limit, that's sine of pi halves, which is 1. Okay, so this cleans up nicely. So I have integral from 0 to 1. Cosine t dt, that's just du, over rad 1 plus sine squared t, so that's rad 1 plus u squared. I want this longer so it matches, right? Aesthetics is important. Good. Now, pretend this is a new problem. You were just handed this. Oh yes, it looks like a perfect time to use a trig sub. I've got radical 1 plus u squared, that's time to use tangent, yes? So we've got u equals a, which is 1, tangent theta. So then du would be secant squared theta d theta. And let's get our new limits of integration. So if u equals 0, the lower limit, that means tangent of theta is equal to 0. Remember, you're not plugging it in. Be careful. So that means theta is 0. And then for the upper limit, where u is 1, that would mean tangent of theta equals 1, which means theta would equal pi over 4. Ooh, looks good. So now let's change our variables. The limits are 0 to pi over 4. Du gets replaced with secant squared theta d theta. And then in the denominator, I have square root of 1 plus tangent squared theta. Well, square root of 1 plus tangent squared theta. 1 plus tan squared theta is secant squared theta. So in this whole denominator, I have absolute value of secant theta. Let me make the squiggly for the whole thing. So this whole thing is absolute value of secant theta. But remember, I know that it's going to be positive based on the restriction. So we have here integral from 0 to pi over 4 secant squared theta d theta over just secant theta. Nice, so I can cancel out one of those secants. And then now we're pretty much home free. I've got integral 0 to pi over 4 secant theta d theta. Did you memorize it? I hope so. This is ln absolute value secant theta plus tan theta. And we're evaluating from 0 to pi fourths. Okay, upper limit first. So we've got pi fourths. Secant of pi over 4, that's going to be rad 2, plus tangent of pi over 4 is 1, minus, I have natural log lower limit, secant of 0, that's 1, plus tangent of 0, 0. So rad 2 plus 1, that's not negative, so I don't need the absolute value. So I have natural log of rad 2 plus 1. And then minus natural log of 1, that's 0. So we're done. That's it. ln of rad 2 plus 1. Box it and call it a day. So that concludes the lesson on trigonometric substitution. Just make sure you memorize and recognize the cases. You've got those trig identities down packed, and then you should be good to go. So don't forget to give the video a thumbs up, subscribe if you haven't already, and stay tuned. We've got so many more integration tricks coming your way.